Welcome back to Calculus 2. We're starting chapter 8 on sequences and series. It's going to be awesome. No, epic is the word you use. Epic. This is now discrete mathematics. And let's first let's start immediately with the definition of a sequence that you should know at all times. Hint, hint. Sequence is an ordered list of numbers. Sequence is an ordered list of numbers, and here it is, the word ordered, underlined twice. The way we order would be through set n, which is natural numbers, counting numbers. You can start with 0, 1, 2, 3. We usually start with 1, well, 1 or 0. These are counting numbers. Don't use negatives. We could, we don't. In some cases, you might have to. And notation would be an in these braces, and braces we know denote sets. So I can write this collection of, let's say, 1, 4, 9, 16, 25. Well, this is the wrong color. 1, 4, 9, 16, 25, 36. Wow. What's after 36? Which? So this is one of the examples, and I can actually write this as n squared, and I can define this n, an, as n squared. So you see all of the notation now together. You have it written as a set, right, in set notation. You also have written as a formula over there that you can use to generate all of the terms inside the sequence, inside the set. So each one of these are terms. And the first one over here could be called A1, and then A2, A3, A4, A5, A6, and so on. And you can clearly see this ordering being done through numbers that are in a subscript, which is 1, 2, 3, 4, 5, 6, which is the counting numbers. So you will be using those values to generate each of the terms. So if I go with the next example, let's say an is equal to 2n plus 3. Well, if I am starting with n equals to 1, right, for the first term, n equals to 1, so a1, I will have 5 as the first term, because n equals to 1, 2 times 1 is 2, plus 3 is 5. And then when n is equal to 2, we have 7, and then 9, and then 11, 13, 15, going on forever. So we can use this formula to generate the entire sequence. And I mean, you can't generate the entire sequence because it's infinite, but you can show enough of these values. So let's practice this. Here's the Bn. You can have Cn, Dn, whatever. The name is whatever letter is available. How about n minus 1 divided by 2 to the n? So generate like 5 terms, let's say. Go with 5 terms.
Starting with 1.
Starting with 1.
1, 2, 3, 4, 5.
Yes.
Not entirely too easy. It can be something horrible.
Yeah, it's every Halloween something's easy, something terrible must happen soon. Run, flee. So we start with 1. It's going to be 0 over 2, then 1 over 4.
1 over 4.
Then when it's 3, it's 2 over 8, which is 1 over 4, yeah. And then after that,
3 over 16.
3 over 16,
1 over 8.
1 over 8. So we generated the first 5. You can simplify this. Sure. And so on. Great. So ordered a list of numbers.
So you would write that as 0 and 2, not as 0.
I'm sorry?
You would write that first one as 0 over 2 rather than 0?
No, we can write it as 0.
Okay.
Recurrence relation. Recurrence relation would be when you have to use the previous term or previous few terms to compute the next term. So you would specify a place to start. Oops. You would specify a place to start, and then you would compute the next term using few previous terms. So let's say the definition for that would be an plus 1 is equal some function of an. So I can give you an example of the recurrence relation. So say that an plus 1 is equal to 2an minus 3, and we start with a1 is, let's say, 7. So you have to also specify what the first term is, because now we're not using natural numbers as inputs to compute each value. Now we are using the first term in the sequence, and then we compute the next one. So when a is equal to 1, we can compute a2 now as 2 times 7 minus 3, which is 11. Now that you have A2, you can compute A3 by 2 times 11 minus 3 is 22 minus 3, which is 19. A4 would be, again, you use the previous term, which is 19. So 2 times 19 is, very good, minus 3 is 35. And let's do one more. A5 is going to be 3 times 35, which is 70, minus 3 is 67. And we can go on and on and on. This generates a sequence 7, 11, 19, 35, 67, and goes on forever. So the difference between recurrence relation and the standard model there was that when you have the standard setup, what you use is you use the set of natural counting numbers. Generally start at 1, but you can start at 0 if you need to. And you use those numbers to compute in the formula. And I'm going to actually just write on the board here so it's, say, close to clear. So AN is equal to, let's say, 3n plus 1, and then AN plus 1 is equal to 3AN plus 1. So the difference between these two is actually, I hope you see it, the difference is in input. This one takes numbers 1, 2, 3, 4, 5, 6, 7, 1 at a time and computes the entire sequence, where this one over here takes the previous term to compute the next term. This n plus 1 means the next term. So if this is A3, then n is 3. 3 plus 1 is 4. So there will be A4. A4 is equal to 3A3 plus 1. A8 is 3A7 plus 1, and so on. So you must have all of the terms before that one to compute. Same like with derivatives, right? In order for you to calculate third derivative, you have to have second derivative, right? You can't jump from the first derivative into fourth or seventh, right? You have to figure out all of the previous ones. Now let's z to the x, right? What's the 15th derivative of e to the x? There we go. You see, this math is easy, right? Nothing to worry about. You can calculate 15 derivatives like this. Oh, there are others. Great. So now, one more thing before we go and start our tests and things. Sequences can be finite or infinite, and we generally worry only about infinite sequences because they give rise to infinite series, which are the ones that are interesting. Sequence can be finite or infinite. So finite sequence is the one that ends up with no dots. So let's say you have good old 1, 4, 9, 16, and there are no 3 dots. So you only have these 4 members in a sequence, and it stops. Infinite one is the one that is interesting. 1, 4, 9, 16, 3 dots, going on forever. Just a definition. And now, sense the tone. Limit of the sequence. So, limit of the sequence. We use limit as n goes to infinity of an to claim convergence, or divergence of a sequence. Very simple examples. If an is equal to n cubed, I can test whether the sequence is convergent or divergent by simply sending n to infinity. We're going to get infinity, which is divergence. Only if the limit goes to a finite value, in that case, we have convergence.
So the only time you have convergence is when you have a finite sequence.
When you, no, you can have infinite. I'm going to write an infinite sequence now. And what's the limit as n goes to infinity of 1 over n? 0. So this one converges to 0. It was infinite sequence because you can plug in n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? You can go infinitely far. So this sequence is infinite. The sequence is infinite. So we have divergent and we have convergent, and every problem will pretty much end like this in your course, in your chapter 8 in this course. So I'm skipping the part on series because this book is a little bit strange how you arranged everything. So we're technically done with 8.1, which is introducing the basic idea of the sequence, and it's introducing as well the some of the most important terminology and most important ideas. And now when we move to 8.2, which is again titled sequences, we're going to see the basic properties and importance of these. So I'm just continuing. Maybe I make a note that we are kind of shifting into section 8.2 now. But we're talking about sequence in depth. So we still use the limit of a sequence to find the convergence or divergence of the sequence. Before we go on with any of these, I would like to show how graph of the sequence looks like. So yes, you're going to have your x and y, but they are now labeled as n and an. Tick marks 1, 2, 3, 4, 5, 6, 7, and so on. And let's say we are working on the sequence an is equal to 2n plus 1. So what's the graph of the sequence? It's the series of discrete dots. You don't get to put a line, you don't get to connect those dots. So for 1, we have what? 3. 5, 7, 9. Now observe what I have there. There's just dots. They're not connected with any lines because there is nothing between 1 and 2. There is void there. So you don't get to compute an at 1.5 or 7.1. An is only computed at integers, 0, 1, 2, 3, 4, 5, and so on.
So in between is basically empty space.
Yeah, I call it the void.
Oh,
Well, it's fitting today to call it the void, right?
it's also the title of a Star Trek fan joke, so
Yeah.
in case I wasn't being lesbian.
We also can check for the convergence or divergence of this sequence by placing it in the limit. We get infinity, we get divergence right away. And we can see that this series of dots actually does not fall onto, let's say, the number line, or does not have a bound to approach. But I want to do one more example. How about this one? an is equal to 1 over n, right? So we have a graph for that. And I will use 4 squares as number 1. So as we figure out the values, 1 over n, it will be 1, and then a half, and then when you plug in 3, right? 4, 1/5. So 1, half, third, fourth, fifth. It's clearly going to go down term by term, right, of the sequence. It is falling down. And hopefully, as you can see, hopefully you see that it approaches the number line, right? Call it the x-axis, but it's a number line n. And if you test this using the limit to see whether it converges or diverges, it clearly converges to 0, because the values have tendency to go around y equals 0. Again, there is no function line through these points. There is void in between each point. The only things that exist are number 1, and then nothing, and then number 2, and then nothing, and then number 3, and so on. So you do not have 3.1. There's no pi in this case, because pi is not one of the integers. It's no e. So now that we take care of that, we understand convergence, divergence, and graphing better as a series of dots rather than the line. We can talk about limit laws for sequences. And this is where we are going to have those limits pretty much repeated from what you guys saw in Calc1 at one point. So this one tells you that if you have two sequences that are added together, you can test them separately, or subtracted. You can test them separately and then put all of the stuff together. So that's the first one. The second one is the constant multiplication. So if you have C times AN is the same as C times AN. Which is C times A. Oh, by the way, maybe I should define this on the side, that the limit of AN is A and the limit of BN is B, so that there is no confusion of what these capital A and capital B are. So those are just the answers. If I am to, here, let me just scroll the other example. So you see this AN over here would be this as AN. So what's the capital A? Capital A is this answer over here, which is 0. So if I have two sequences added to each other, I can add them algebraically if that's possible and then find the limit, or I can do each one separately. So A and then B. Three. Purple. Yes.
So if you were gonna add the two that we did and you get a divergent and convergent, what happens?
Well, anytime you have a divergence somewhere in there, has to diverge, yes. It's going to mess up everything, right? So any combination with. Now here's the one that works with limits but not with derivatives and integrals, right? So the product actually just goes into product of the answers, and then we have the quotient as well. So this is just for us to take those limits. And now, what is the limit as n goes to infinity of n plus 5 over n to the n? So try this one on your own. I hope you reviewed limits, right? And if you haven't, well, you're going to burn out over it.
Yeah. Of 1 to the infinity power. Yeah. It kind of just converge to 1. Well, yeah, if it starts at 1, it starts at 5. And then it's 2. So it starts at 5 and then it goes to infinity. It does. Well, just to plug in 0, it doesn't work. Yeah. Plug in 1, 6. Alright. It definitely goes into That's something I'm trying to work on right now because I can program it, but to make it really aesthetically pleasing, it doesn't make it short. converges to 0. Well, how do you plug in for 6? That's the whole thing.
Let's take a look at this problem. So, say that your sequence looks like this. And the question is, does it converge to a finite value or diverge? Converges. To, no, no, no. They can't converge to infinity. Only those people who buy infinity can converge to infinity. Other than that, no.
I'm totally missing the concept.
Yeah. So let's discover the way. So you all are familiar with taking basic limits. That's okay. Now this is a little bit spicier situation. I will start by defining this. And I will ln both sides. So now what I have is ln y is equal to n ln of n plus 5 over n. And I can put the limit in front. N goes to infinity. Now what I'm going to do is I'm going to rewrite one more time but this time around I'm going to write this as n times ln of 1 plus 5 over n. I mean, if you wrote this one as 1 plus 5 over n raised to the n, you need to know what this is because you are in Calc2. But the reality is, right? So now what do I have? I have infinity times 0, and if you remember your L'Hopital rule, you can work with this using the trick f is equal to 1 over f. So we have ln y is equal to the limit n goes to infinity of ln of 1 plus 5 over n divided by 1 over n. And now what you have is 0 over 0, which is called the indeterminate form, which means that you can perform L'Hopital's rule when you take derivative of numerator and denominator independently, and the limit would be equivalent to the original problem. So now limit, we'll place this L apostrophe H, go n to infinity, and we take these two derivatives. So for the derivative of the top, right, the numerator, it's ln, so we are writing the function as is, and then we take its derivative in the numerator, which would be negative 5 over n squared. And on the bottom we have just negative 1 over n squared. So here's your want to call this a double fraction or a quadruple fraction or whatever you want to call it, we are going to multiply, well, yeah, which is, yep. There's also, I could do over 1. Nah, maybe too confusing. So let's multiply n, negative n squared, and negative n squared. Whatever you need to use to solve this algebra, that's up to you. So what do I have? The denominator completely cancels. I'm only left with the numerator, which is negative 5 divided by 1 plus 5 over n. And as you send n to infinity, this term goes to 0. So we have ln y is equal to negative 5. No, that's a positive 5. Because we multiply by negative, so that goes away. So since ln y is 5, that means that y is equal e to the 5, which is exactly what we were looking for, the limit, right? So to avoid this particular calculation for one of the most frequent situations, because the application is so vast for it, you might want to memorize now, so you don't have to go through this every single time. Of course, you will have to do L'Hopital limits throughout this chapter, sure, and you should review that. But you will just make your life so much easier if you memorize and recognize this form every single time. So whatever number is above n, which I call r, that will be the exponent of e. So in our case, it was 5, so we have e to the 5. Remember this.
So it's basically whatever the L and Y would have turned out to be.
So now we have some terminology to take care of. So sequence AN is increasing if the next term is larger than the previous term, right? AN plus 1 is the next term after AN. Remember the void between n plus 0 and n plus 1. There's nothing in between. So these are definitely two consecutive terms. So increasing means that the next term is bigger than the last term, the previous term. AN is non-decreasing if AN plus 1 is larger or equal than AN. So observe the difference between increasing and non-decreasing. They're not the same. They're not the same. Because remember the sequence we had earlier where that 1/4 or whatever number happened twice? There it is. You see you have 0, and then you have 1/4, and then you have 1/4 again, and then 3/16, and then 1/8. So looking at this, there is a repeat right there. That is that equal sign kicking in. Where this one is strictly increasing. Strictly increasing because 5 and then 7 and then 9, there is no need for equal sign anywhere. But the one on the bottom does need an equal sign because 1/4 is the same as 1/4. And you have this now terminology which calls the one on the top increasing and calls this one non-decreasing. You see, because if it's non-decreasing, it's easier to say because non-decreasing means it could be increasing and same, right? That means non-decreasing because you actually have three things that can happen: increasing, decreasing, and the same, right? So saying that something is non-decreasing means that it can increase and also be the same at the same time. Yes?
Wouldn't it be non-increasing then? Just going down.
Oh yeah, this one is non-increasing. Yes. You're right. Well, I'm going to now define the other two. So we have an is decreasing if an plus 1 is less than an, and then we have non-increasing. So non-increasing. Then we have monotonic if it's either non-increasing or non-decreasing. And finally, an is bounded I'm going to underline these important words. If there is number m such that
The men, number n.
m such that the sequence is always either smaller or bigger. So convergent sequence that we had 1 over n was bounded below by 0. Yes.
Can you explain the last one? So it's bounded such that the absolute value of an is less than or equal to.
Thank you for the question.
What's an example of that?
I'm going to give you first the graphical example. This line would represent a bound. Bound, which means that the function will not cross it.
Like an asymptote.
Perfect, horizontal asymptote. A theorem, it says a bounded monotonic sequence always converges. What happened? I can tell you right now. No. This theorem here might be understood as a common sense consequence of the graph you have above. It's a bounded monotonic sequence. What it means monotonic? Monotonic means it's always either increasing or always decreasing. So you see this one is always increasing and it's bounded, so it has to converge to the bound M.
I have a question. Monotonic, if the sequence is either non-decreasing or non-increasing.
Yes. Non-decreasing or non-increasing. That's the monotonic part.
Okay.
That just means it has this trend of going always up or always down. With some values might be the same,
Okay.
but it will never, I will never skip a step, it will never lose a step.
So for the bounded definition, I mean, you have a less than or equal to. Do you also have the greater than or equal to?
We have absolute values on AN, which takes care of the both cases.
So it means just a bounded, it doesn't always have a conversion.
Yeah, because it can be bounded from below, like let's say e to the n. E to the n is bounded from below, but unbounded above, because it would look like this. Right? So there is a bound here, which is the n-axis. It will never go below, but the top is not bounded. So that would be, right? So we have to be a little bit careful about that.
So the general overall shapes of these things follow how the functions look.
Yeah.
Except that nothing is in between is still there.
Yes. So it's, you can literally think about every single one of these when you get an. How does an as 1 over n, how does it look like? Well, it looks like your 1 over x graph, but it's just dots, right, with the void between each one.
So this can never be negative.
I'm sorry, what do you mean?
Like, could you have a negative number?
As the result? Yes, yes. I can have negative numbers as the result because I can define an to be, let's say, n minus 20.
But n cannot be negative, right?
Yeah, we don't use negative n's. Because it's generally what you have here is a step forward in time. If you want to think in terms of the computer science, writing a program or algorithm, you start at the present and then you go forward. So the time ticks 0, which is now, right? And then you go to the next second and the next tick and the next tick. So that's why you don't consider any of the negative axes. It's just, and also the definition for a sequence states that it is ordered list of numbers where ordering is done to set of natural counting numbers. We are technically not supposed to even let the 0 in, but you say, come on. It's okay. It's okay. We have plenty of ways.
There's no negative exponents. No negative exponents.
Yeah, we can have negative exponents on the, no negative input n values.
No, okay.
Yeah. Then again, you can shift things and sure. Negative one is going to creep in general, yes. I have 5 minutes, or I have 5 minutes and then another 40 after that.
5 minutes.
Oh, 5 minutes and another 40? Awesome.
You have 5 minutes and another 35.
Oh,
So you have 40 minutes total.
Oh, right, you're right.
oh, he's right?
Yeah.
Damn, actually good to be on Apple time. How much did you pay for it?
$300.
That's what I pay for my kid.
Yeah, see,
But
apple
the
time
bandwidth-
expensive. All right. So something that will save your life in terms of certain limits. Growth rate of sequences. Growth rate of sequences. So you are going to run into a sequence which says at some point an over bn as n goes to infinity, and you will be scratching your head to figure out how, comma, in hell, comma, to take that limit, because you are not sure. Well, if it falls under this category somehow, you will be able to just look at it and make the conclusion if you know what's the growth rate of these functions. So you can either have answer to be 0 or infinity, nothing else. So it's either 0 or it's infinity, because you are taking functions that are not of the same kind. So one will grow faster than another. If you have faster growing on top, it's going to go to infinity. If you have faster growing on the bottom, it's going to go to 0. It's always like that. So this can swing going to 0 or infinity depending on the... Actually, you know what? Let's do it this way. An is always the first one, so equal to 0, or limit n goes to infinity of bn over an equals to infinity. So now what are these? Well, we start with the sluggish one first. It is ln to any exponent of n. That's going to be smaller than any polynomial.
I'm sorry, what is that ln squared?
Q.
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 Oh, Q.
Q. Lowercase q. Happy. Makes it beautiful. Something that you had to explore. And then we have n to the p ln qn, which means when you multiply polynomial and ln, which will be less than any polynomial multiplied by another polynomial.
Why do you have two less than?
That means that they are forever less than. Oh, sorry, eventually will always be less than, eventually. And I'll show this right now, which is less than
Oh my gosh.
b to the n. There is no 5 anywhere. It's s, which is less than the factorial, which is less than n, which is less than n to the n. And we reach the end of this list. It is very simple to use this list. As long as you know which one goes first, you kind of put these things together. So you see that n to the p, right? That's a polynomial piece. And then you have two polynomials multiplied with a p plus s. And then you have exponential ones, b to the n. And then you have the factorial. That's the one that you didn't probably see yet. And we'll have to discuss that one. And then what I call the boss, which is n to the n. So I'll come back to explain this and show examples after this talk that we need to have with regards to factorial. It's too much. So what you see here is not n, right? It's just n with the exclamation point. This is the mathematical notation for certain situation. Let's see. Immediately I'm going to define this n factorial. So there's no need to scream. As 1 times 2 times 3 times 4 times 5 times dot 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 times the previous term times the last term, which is n. That's what the factorials are. So what would be 6 factorial? Which is equal to? Very good. Yeah. Very good. Fibonacci sequence came up. Fibonacci sequence is a recurrence sequence because you have to take previous 2 values and add them. I could talk about Fibonacci sequence later.
No, that's fine. That was part of this whole thing.
Yeah.
This whole concept set.
So we understand the 6 factorial. Now, there's another cool aspect out there of these factorials, and that is that you can write n factorial as n times n minus 1 factorial. Or you can write it as n times n minus 1 times n minus 2 factorial. Or you can continue creating these formulas forever. Now you might ask yourself, what the hell is this? Well, here, what the hell is this? 5 factorial is the same as 5 times 4 factorial, and this should make sense immediately, as soon as I write it. Does it?
Mm-hmm.
5 factorial, look what you have. Right? You peel off 1, and then all of the other factorials are still there. You could write them as a. So this is 1 times 2 times 3 times 4 times 5. This one over here is 1 through 4 multiplied, and then you have your 5 there. This is 1 through 3 multiplied, and then you have 4 and then 5. Right? Does it make sense? You will need this a lot in this chapter and the next one. This is crucial to know how to break these factorials. You will not be computing these things.
After writing recursion algorithm for factorials in the class.
See?
What are you going to be doing, like calling off some and canceling them? And then leave that?
Yes.
So when you mentioned this was about computer tech, what you're basically saying is this is how the programming interfaces the computer with the computer.
Well, how the software is written. It's how software is written. Uses this stuff. Okay. Now I'm going back. So back to growth. Great. So what I want to do here is show off some of the values and how and why growth rates work as they do. This is n, this is 2n, this is n squared, this is 2 to the n, this is n factorial, and this is n to the n. These are all key points. I didn't put the logs because we know logs are sluggish. But you can see doubling, and then squaring, and then exponential, and then factorial, and then n to the n. So let's compute the chart for 1, 2, 3, 4, 5, 6. That should be good enough. Clearly, when you double each one, that one grows faster, right? So that's why 2 to the n is growing faster than n. Now n squared is 1, 4, 9, 16, 25, 36. And you see how n squared beats previous, right? But it started sluggishly, right? It started less than 2, then it equaled it on a 4, and then it beat it with 9, and then after that 16, 25, it just took off. 2 to the n.
Acceleration. Basically, right? No?
Nope.
No, okay.
So 2 to the n. 2 to the n is 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. So it's kind of losing, right, to n squared. And then 16, it's catching up. And then 32 and 64. Look at that. This is why they say grows exponentially, right, in a figure of speech. Well, you'll be able to actually do better than that. Because look at 64, how it took off in respect to 6 and 12 and 36. Now we go with factorials. 1 factorial is 1. And 2 factorial is 2. And then 3 factorial is 6. Slow. 4 factorial?
124.
Boom. 5?
120.
Uh-huh. Look at that. Look at the growth in factorial. And now n to the n, that's just crazy. 1 to the 1 is 1, 2 squared is 4, 3 cubed. Look at it, look at on a third term what then n to the n does. Fourth, 256, very good. It's 16 squared, 256. And then you have 5 to the 5. 625 is to the fourth, and then you need to multiply that by 5. So it's 3,125, right?
Yes.
Whatever I say. Awesome. I want everyone to bring cookies next class.
Don't you have any
Chocolate
cookies
chip
at your
or-
desk?
Yes, I do, but I already ate those.
You ate all of those?
Yeah, I ate the whole plate.
OMG.
Yeah.
What type of cookies? Chocolate chip?
No, there was like those Italian ones with all the different sprinkles, chocolate sprinkles and everything.
Oh, yeah, I can eat that.
I'm a professional. What's the 6 to the 6? Who calculated that? You have the calculator. 6 to the 6?
46,656.
There we go. Yeah, I think you will win, right? So now you understand what the growth of these means, right? Observe that first 3 are all polynomial. This is the first order linear ones. This is a constant above this. And then you have a square, which is still within the same realm, right? But still grows faster. And then you have the exponential, and then factorial, and then you have n to the n. Now, when you see this type of a growth, this is what's happening now. If I have, let's say, a limit of 3n factorial divided by n to the, let's say, 4n, as n goes to infinity. Clearly, it must be 0, because you have slow over fast. Why do I say slow? And factorial is not slow, but it's slower than this one. So when you have slow over fast, that means that this one is going to infinity much faster than that one. So it pulls everything to 0 because you are dividing smaller numbers by huge numbers, right? So it's going to 0. And if I'm to flip this, the answer would be infinity. Yes?
That's a 4n on the bottom?
Yes, n to the 4n. 3n factorial is going to be, in this case, infinity. So this is not mathematically correct, but limit as n goes to infinity. Guys, you have to send n to infinity. You can't send it to 3 or 0. It has to go to infinity. So if you have slow over fast, we're getting 0. And the limit n goes to infinity, fast over slow, we will have infinity. So, and I will put this in quotation marks because this is not mathematical notation, but it helps you remember these things so you can solve a whole bunch of the limits that you know faster. Yes?
So if you had something like say 3 3n factorial over 3n factorial, and it just goes to 1. So that's
The limit is 1 and converges to 1.
Okay, gotcha. And that would defy the rule that it's on t to 0 and infinity.
Yes, but the trick is that we are learning here growth rates of functions. See, if you have the same ones, 2 polynomials, we don't need any of this stuff. Because you can solve it within the realm of polynomials through cancellation or stuff you learned in chapter 2 in calculus 1.
Sure.
I'm asking what's going to happen when you mix polynomial with e to the x. There is no mathematical manipulation that you are going to use to combine in any way polynomial with a transcendental function like ln or e to the x. Or in that case, you need to know that x is faster than ln x, x is slower than e to the x, and you can solve these limits quickly. Otherwise, you're doomed. There's nothing. I mean, you're not completely doomed because in most of those cases you can use the L'Hopital's rule,
Okay.
which takes a page, all right? So learning this might help greatly. Now I'm going to skip from, so this is it for 8.1 and 8.2. I'm going to skip concept of the series because I'm going to start, 8.3 is called infinite series. So I'm skipping concept of a series and I'm skipping geometric and whatever else they had in terms of series because, sequences, because we do have, all of that stuff is in 8.3 again. This book did an awesome job of mixing everything up. So that's all I had to say for this, unless, let's do one more example or 2 more examples as a review of everything.
Can we look at L'Hopital's rule? Yeah.
Yes, you will flip on page section 4.7, or look at one of the 60,000 YouTube videos that are available. But it might pop up with what we want to do. So yeah. Let's see. Oh, and there's also squeeze theorem for this. Remember that one?
God, I hated this quiz thing.
Awesome. Look it up. Awesome. Look it up.
That concept.
Look at all of these wonderful examples that you're going to work on for homework. I mean, yeah, this is the book, but the MyMathLab is the same question pool. Okay. So polynomial, slower over faster, 0. Boom, done. Same.
1.
So
1/3.
1/3. Awesome. Same. 3/2. Look how you do these limits, huh? You see that? Do you feel the power?
So same over same is 1 and then times the 1/3.
Yes.
Okay.
E to the n, 2. 3. Ooh. It will be 3. Nice, because this n plus 1, that's like 3 to the n times another 3 there, right? When you peel off the plus 1. That is something that you must know, otherwise you are dead in this chapter. So, that was invisible ink. Just to kill my momentum that I had. 3n plus 1 can be written as 3 times 3 to the n, because that's that 1 and then exponents add, right? Do we remember algebra? So that's how this limit over here ends up being 3. Forget about this. This is nothing's going to do anything there. This is the one. They're same. How about here?
1/9.
This is so cool.
1/3.
1/3. Yes, 1/3. Do we see 1/3 there?
Yeah.
Yeah, we see 1/3, right? Because when you stand sufficiently far, this plus 1 is not there. So square root of this is 3k. K over 3k, 1/3. Awesome. Ooh. This is the one that we just need to know because we are on this planet since Precalc2. Pi over 2. You might want to write this one down. So pi over 2.
So
And
you're saying that's the answer to that?
oh yeah.
Okay.
Do we all remember 2 months ago when I drew the graph and I said, remember the arctangent is going to pop up? There it is, popping up right now. There's your pi over 2, right? The limit as x or n goes to infinity. Right there, that question. This one.
Oh.
Ooh, spicy.
0. Infinity. And
So this is one of those L'Hopital rules that you love, right? Where you have infinity minus infinity, and then the answer could be 0, could be infinity, or 3/4, right? Depending on how the functions line up. So this is why you should really spend time reviewing L'Hopital rule section with improper. So you have 0 over 0, infinity over infinity. Those are the two indeterminate forms. But then you have 0 times infinity, infinity minus infinity, 1 to the 0, 0 to the right infinity, and all of those flavors, which use ln's and other voodoo. So think about those. So I'm telling you, 16 L'Hopital rule. Try it and see how you can do it. How about this one? Nope. 0. Tangent to the -1 is going to get stuck at pi over 2. But the bottom is going to go, what, pi over 2 is how much? How much is pi over 2? 1.5. Awesome. And what is this doing? 1, 2, 3, 4, 5, 6, 8. So the top is stuck at pi over 2. That's it. That's the bound, pi over 2. The bottom goes to infinity, so 0, right?
yeah.
0. Ooh. That's another L'Hopital, right? You gotta use ln both sides, drop 2 over n in front of the ln, and then use the magic, just like I did in the example over there that had the E answer. This is, well, you should know now this one. You just look at it and you say E squared, yes, E to the 2. This is the, what? Nope. Gotcha.
Either one that is 0.
5 is on the wrong spot. All right, if plus 5 was up there, that's the problem I did, right? So e to the 5. So this is, this is equivalent to the, because, yeah, plus 5 on top is the one for the to be into the 5. This one you actually have to take a look. But then again, right, that's 1, but then it's 1 to infinity right there. Now what's 1 to infinity? Oh, really? It could be E also. Depend on the function. Gotta do L'Hopital rule. I have no clue what the answer is until I... No, I don't. I have to do it. So I have to put ln in front. I have to peel off this one and then do the derivatives and see what it comes out to. There's no way around it.
We'll do that one.
Yeah, you can. Ooh. Awesome one. That's awesome. This one crazy. So you see
Wait, that's 0.
what? This one?
Not the sine one.
Sine 1? 0? Why would that be 0?
1 over infinity is 0, sine 0 is 0,
And then infinity times 0 is? Is it?
What happens with infinity times 0 is 0?
Really? The answer to that is no. 0 times infinity tends to be e to the 5 in some case. Remember the example I did? Was that 0 times infinity? I'm gonna scroll because it's just so awesome. You will have to see. That's there you go. Now you can see. So see 0 times infinity, and the answer turned out to be e to the 5. Yeah. With calculus, this notion 1 to anything is 1, and 0 times anything is 0 actually goes away. Because, and also infinity minus infinity, a lot of people will say 3 minus 3 is 0, and 5 minus 5 is 0, infinity minus infinity, 0. And I say, nope, here's the example with 3/4. Right? So, yeah, some of those examples, guys, that you get will be, 3/4 or something like that. So you really have to be careful what they are, and then you will eventually get it. Let's jump to the book one more time. You have those wonderful examples, and then you have these ones with -1 to the n. And I would like to talk a little bit about that, because we are going to see, what do I have, 3 minutes and then another 10 after that? Awesome. Is the Apple time aligned with the cheap time?
As long as the Calc time is old now.
Yeah, that's why I'm wondering why would people pay $300 for it when you can get one for $1.
Because it keeps track of my fitness.
Yeah, that's
Oh.
probably the reason I have mine.
All right, I really
It
cannot.
also helps me find my iPhone when I've laid it down somewhere and walked away.
That helps
Bring
me to
up-
breathe.
yeah,
It's
I-
kind of 20 minutes.
Yeah, see, it only takes me a minute. I just have to, what I do is I pull up the music and play something and I hear it play.
Oh no, there actually is a beam that if you just swipe up,
I'm sorry?
it's like a phone with like pulses, you can just tap that.
Oh.
I can show you.
No,
Yeah, see all the stuff that I want to know.
I haven't updated to the most recent.
Oh no, it's on all
Well, okay. So you're gonna do number 32?
No, I was supposed to do something I forgot. Oh, -1. Thank you. See, that's wonderful. -1 to the n is called the alternating term. You're going to have a whole section, 8.6, talk only about alternating series. So this alternating term is extremely important. Clearly, it's going to go when n is equal to 1. So -1, 1, -1, 1, -1, 1, -1, 1, and it's going to go like that forever. Clearly bounded above, clearly bounded below. Does this converge or diverge? What do you think? What kind of answer is that? You might as well said Thursday. Does it converge or diverge? It diverges. Diverges, yes. It diverges. The reason is, right, it does not go towards a single value. It hangs around +1, -1. There are some more advanced mathematical techniques that we are not going to cover in this class, like subsequences. So you can figure out that something diverges if you have two subsequences which approach different limit. So I can pull out a subsequence of every other number would be -1, and that approaches -1, and then every other number would be 1, which would be approaching 1, so you have those two competing values. It's just like for the function, right? You can't have two y's for a single x. So within this realm of sequences, you can have two different limits within the same sequence. So this one definitely diverges, right? It's called the divergent. It's not converging, right? So therefore it's divergent. And it's extremely important. Now I want to call your attention to cosine n pi. Cosine n pi. When n is equal to 1, what do we get? We get -1. And when it's 2, and when it's 3, you see the tricky way of writing the same thing? You got to be careful about this one. See, sine doesn't do this. So sine n pi is just 0, 0, 0, 0, 0, 0, right? So sine n pi is just a whole bunch of zeros. Over 2, yeah, sure. But sine n pi is just going to be a bunch of zeros. Where cosine n pi gives us exactly the alternating one. So they're going to hide this alternating term sometimes in your homework examples and so on under cosine n pi. So you have to be careful about that. Bueno? B. So then they just try to be as obnoxious as possible, as you can see in problems 82, 83, 84, and 85 in the upper right corner. Right, it's just annoying. So, how would you do this? 82. How do you do 82? 5, like this. Anything is possible, exactly. You can be the president. Well, actually, no, some of you can't.
If you split up like you can, so you have 4n over n factorial plus n.
Okay. So you can do that, right? You can split, and then that's slow, that's fast, so it goes to 0. And then the second one, they have the same, so just 5. But you can also train your eye to look for the largest, the fastest one. On top, and just focus on that one, and look for the fastest one on the bottom, and focus on that one. Completely ignoring 4 to the end and 2 to the end because they're... I'm sorry? Yeah. So you kind of filter anything that is lesser. So, how about here?
Wait, number 82, the answer really is 5?
Yes. The answer is 5. How about 80? What happened? 84? 0. We clearly have in our, right, slow, fast, and so on, that this is slower than when you take the same thing and multiply by ln, right? So that's faster than this, and that's stated on the string that I gave you. So this is slower, fast, 0. Awesome. And now how about this one? What do you think? So there are 3 options, right? Infinity, 0, and then 7 over 5. It's gonna be one of those, right? So if you write all 3, hopefully I'll pick the right one and just, right, take off 2 points and then be done, right? Because you wrote multiple ones.
Is that actually a thing? Like, do we do that?
No. I don't know why I even said that. That actually a thing.
Yeah, we did all of that stuff.
So you'll figure out 85 because you'll enjoy that, right? You'll figure that one out. And I'm just consider this thing, and see if you learn the rules and properties and definitions and all that stuff, this becomes very easy. It becomes very easy. And you'll figure it out from here. Right? I just point to number 3, and that's it. So for 85, you'll figure out the rest on your own. Sequences by recurrence relation, 86 through 90. They give you the formula, and then a starting term, A0, which means that's going to be A1, 6, half of 5, and then plus 2. No, you're plugging in 5, right? So half of 5 is 2.5, so 4.5. And then it becomes progressively more annoying as you go down. The first term is 0, so if that's 0, that's 0 plus 1 is 1. So A1 is A0, half of A0, so half of 5 is 2.5 plus 2, 4.5. 4.5 over here is 2.25, 4.25. And then it's going to keep doing that. It's going to be progressively more annoying to come up with these ones over and over and over. Where is this squeeze? Where is the squeeze theorem? Thought that was a squeeze theorem somewhere. Hey, there they are. Awesome. Yeah, review that. I know. It's awesome, right? Should I do 1?
Yeah.
All right.
Thank you.
We have 3 minutes. Oh, you walk. I'm awesome, man. Never forget that. You lost so many points with the statement. And because of that statement, I'll do the cheapest one of all. All right, let's go with 56, for instance. That's right in the middle between. Well, it's not right in the middle, but 53 and 58. So 8.2, 56. We are supposed to figure out the limit of cosine of n pi over 2 divided by square root of n. So we will start by good old cosine of whatever, n pi over 2, doesn't matter, is always going to be bounded by 1. The meaning of this statement is that cosine n pi over 2 is squeezed between -1 and 1. Now you use your eyes to compare the cosine here to the function there, and you'll see that what's missing? Divided by root n. So boom, boom, boom. So now what you have done is you created this -1 over root n is less equal than cosine n pi over 2 over root n less equal than 1 over root n. And as you put limits everywhere, n goes to infinity, this one goes to 0, last one goes to 0, which push the middle one to go to 0. That's the squeeze theorem. Just remember the cheese between 2 pieces of bread, and if you're lactose intolerant, 2 pieces of cheese between the bread. That's what the squeeze theorem is, right? Whenever you bring the bread, the cheese has to go with it. So that's the cheese right there. So we build up from the trig function which always has to be bounded by 1, so whether it's sine or cosine doesn't matter. It's always stuck between -1 and 1. And then, because that's the range of sine and cosine, -1 to 1. You can also have arctangent, which is from -π/2 to π/2. Do they have any arctangent there? Oh, yes, they do. 57. So just be careful of the range, right? So the range will cut it off, and then you build the rest of the function around. You start there, and then add whatever is needed around it. Very good. Well, that's it. That's it for today. Maybe that should be, you should do the study plan for it without me assigning the homework, because people will be freaking out.
You should have to do that.
Yes. So when you go into My MATLAB, sign in, and you are in Calculus 2 course right there. Okay, so what you do simply is you go into study plan right there. You click on study plan, you go here, view all chapters, boom. And now you pick whatever you want. What I'm, is the L'Hopital's rule, 4.7.
Okay.
You click on it, and you will get every single problem that exists in a system. This is the maximum. So you can do this for Calc 1, 2, and 3 directly from your, because it's study plan, yeah. And the grade from here does not impact your overall homework grade, and it doesn't mess with quizzes or anything like that. So it's completely self-sustained, and you have access to every single, you can have, so you can go on chapter 2, do the limits on everything, and I emailed you that we skipped the section because I said to students that you have the list of integrals in the back of the book, because that's what it is. You look up what the integral is, you find a similar one, and you answer the question. And I really can't provide that on a test, the table of integrals. So I can't really put anything from that section on the exam. That's 7.6. So there's no stream for it, there's nothing. And since you wondered the notes, here I'll show you the notes.
He's posting notes right now.
Oh, nice.
That's the notes.
Can I
for
copy it then?
sentence. Yeah.
All right, thanks.
Are they
You are.
posted?
What?
Your notes from tonight?
No.
We're gonna do that right now, right?
Yes.
Are you gonna be in your office on?
How much do you pay?
He's gonna be there.
No, because it's like once he wasn't there.
Once.
Yeah.
And that immediately means that every single time I will not be there. You see, this is how life is never fair. But that's okay. We have to.
It could be the time he was yet again a half an hour behind his time.
Probably, but
Like once you had to go to like I don't know, for teach another class or something. Like
oh yeah, to substitute. Yes, that was the time. That was that time.
that's what it
I was substituting. Yes. I exported notes so far, and I'm now logging into RVCCC. So this is going well.